I'm glad to have the opportunity to make this presentation. The presentation is about the work using text GPS records to plan bus network. Text GPS traces provide us with rich information about the human mobility pattern. In this work, we intend to use the information to plan bus network. Specifically, the proposed framework comprises a method for determining candidate stations by using passenger pickup and drop-off records, a method for generating bus routes and a bus network. To prove the effectiveness of our work, we do studies based on a real-world dataset and show that our proposed framework outperforms traditional ones. As we know, buses are more cost-effective and environment-friendly than private cars and taxis because they help to decrease traffic congestion, fuel consumption, carbon dioxide emission, and travel cost. However, traditional methods for bus network planning and design are usually based on human servers. It's not only costly but also inaccurate. Nowadays, with the application of wireless communication technology, taxis are usually equipped with GPS devices, and we can get real-time and spatial information from text GPS records. In this work, we use the information to plan bus network. Next, I will introduce some main steps of the work. This picture is a description of the dataset. It comprises some important information, such as when and where the passenger get on and off the taxis. Then, in order to get more accurate results in this work, we used the UTM projection to convert the longitude and the latitude coordinates into plain rectangular coordinates. In this stage, we need to decide candidate bus stops by analyzing the text PDRs. The PDRs refers to text passenger pickup and drop-off records. We split the area into equally sized grid cells, and we named the cells which contain PDRs as hot ones. And the picture is an example of hot grid cells. Next, we use the following method to get the candidate bus stops. First, for each hot grid, we count the number of PDRs within 300 meters. Then, we select the grid with the most PDRs as the first candidate stop. Finally, we remove the PDRs within the coverage of the stop. It refers to the circular area in the right figure. And then, for the rest hot grids, we update the number of PDRs within 300 meters. We get next candidate stop and repeat the above process. In this stage, we first need to get passenger flow matrix and time matrix. The matrix represents the number of passengers or the travel time from one station to another. In the passenger flow matrix, we count the passenger flow from the coverage of one stop to that of another. We further calculate the average time between two candidate stops. Then, we use ant colony algorithm to generate bus route. Here are some important definitions in the algorithm. First, we define the visibility as passenger flow between station I and station J. Then, we allocate more filaments on routes with more passengers. In the algorithm, ants randomly select the next stop according to the transition probability, which is affected by visibility and filament. We will calculate the total time of the current route. If the total time satisfies the time constraint, the ant continues to search for the next station. Otherwise, it stops searching and we can get one route. For the current route are like this. We calculate T according to the following formula. The T0 is the waiting time of the bus at each stop. After we get one route, we need to update the filament matrix. We update it according to the following formulas. Rho is filament evaporation coefficient. Delta tau ij is the filament increment. M is the number of ants. K is the case ant. And Q is the filament constant. We will allocate more filament on the routes which have greater passenger flow. For the route are like this. Passenger flow is determined by the following formula. After we get an optimal route, we need to update passenger flow matrix, and then we get a new route based on the new passenger flow matrix. Here is an example. For the passenger flow matrix, like this, we get an optimal route, station 1, station 3, station 8, and so on. And then, we need to update the matrix. The passenger flow between station I and station 3 is set to 0. Based on the new matrix, we can get another route, and finally, we can get a bus network. In this part, we test our proposed approach with a real-world text GPS dataset. The dataset was generated from taxis in New York and comprises more than 3.4 million passenger trips. In the experiment, we get 200 candidate stations. The figure shows the number of PDRs within the 300 meters of these stations. It can be seen that the stations ahead contain more PDRs. It means there are more potential passengers in these stations. And then, as shown in the figure, the PDRs covered by the top 80 stations accounts for 74.29% of the total PDRs, and the PDRs covered by the top 100 stations accounts for 80.12% of the total PDRs. So we decided to select the top 100 stations as candidate stops. To prove the effectiveness of our method, we proposed two indicators to evaluate candidate stations. The first is the total number of PDRs in the coverage of all candidate stations. Obviously, good stations should cover more PDRs. The second is the effective area covered by all candidate stations. Similarly, good stations should cover larger effective area. Next, we compared different candidate stop generation algorithms. The figure shows the comparison results. As shown in the figure, the x-axis represents the number of candidate stations, and the y-axis represents the number of PDRs in the coverage of these stations. When the number of candidate stops is the same, the stations determined by our method can cover more PDRs. It means there are more potential passengers. Similarly, the x-axis represents the number of candidate stations, and the y-axis represents the effective area. When the number of candidate stops is the same, the stations determined by our method can cover more effective areas. This shows that the distribution of stations is more reasonable. Therefore, our method is better than the baseline methods in many aspects. Finally, we compare bus route generation algorithm with the baseline methods. As shown in the figure, the x-axis represents the travel time, and we get one route under this travel time constraint. The y-axis represents the passenger flow on this route. We can find that, under different time constraints, the passenger flow on the routes which are generated by our method is larger. In this paper, we propose a new method for generating bus routes and the network by using the text GPS traces. The proposed framework comprises a method for determining candidate bus stations according to the text passenger pickup and drop-off records, and a method for generating bus routes and the network. With a real-world dataset of 3.4 million passenger trips, we conduct simulations and show that our proposed framework outperforms baseline methods in many aspects. That's all about my presentation. Thanks.